Hello students, welcome to Vista's Learning. I am Harshitha, your chemistry tutor at Vista's Learning. Vista's Learning is an online education platform where we strive to provide quality education for all. So you all are aware of it by now, right? So we have almost come to the end of our fourth chapter, which is chemical kinetics. So today will actually be your last session based on the topics whatever we are going to be learning in this particular chapter. Okay, so before going to today's topic, let's just see what we studied in our previous class. So we learned about how exactly temperature dependence of the rate of the reaction, as in how exactly the rate of the reaction is being temperature dependent, and along with that we studied what is activation energy, right? So what is activation energy? Energy that is required for the reaction, okay, for the reactant especially, in order to cross the threshold barrier, right? Threshold energy barrier, so that it can form the product. So we also studied this particular equation, Arrhenius equation, right? K is equal to, right? So we studied this particular equation. So in today's class, what will we be studying? We shall be seeing what is the effect of catalyst. So how exactly a catalyst is going to affect the rate of the reaction, the rate constant of the reaction. We are going to see that. And what exactly is the catalyst? You all are aware of it already by now, right? So let's just have a recall of that, and then we'll go ahead with effect of catalyst. And along with that, we shall be studying collision theory of chemical reaction. So collision theory, what is collision theory and how exactly is it related over here in chemical reactions? How will we be studying about collision theory? Who came up with collision theory? About all of these things we shall be studying in today's class. So without any further delay, we shall move to our first topic, that is effect of catalyst, right? So what is the catalyst? So catalyst is nothing but a substance which increases the rate of the reaction, right? It increases the rate of the reaction without it undergoing any kind of permanent chemical change. The catalyst won't undergo any kind of chemical change, but like permanent chemical change, but the rate of the reaction is going to be increased really good, really well. So this is something which actually makes sure the speed of the reaction is being increased. So here is the definition: a substance which increases the rate of the reaction without itself undergoing any kind of permanent chemical change. Clear? So there's an example here in front of us. 2KClO3 in the presence of MnO2. Here manganese oxide is going to be our, manganese dioxide is going to be our catalyst, which is going to give us 2KCl plus 3O2. So in this particular reaction, what is the catalyst? MnO2. So here what is happening? KClO3 giving KCl plus O2. If the catalyst was not there, the reaction, okay, the reaction would be quite slow. But with the included, when the catalyst is being included, the reaction rate has been increased. So what exactly do we mean by rate of the reaction is being increased? The rate constant is increased. How can we say that? This is actually correlated with activation energy, which is being decreased. So how exactly does the catalyst do this rate of the reaction increasing factor? How does it do that? If we see, it is basically because of the activation energy. So activation energy, that is EA, decreases. How does the activation energy decreases? That is because the catalyst is being introduced into the chemical reaction. So that is how we can say if the activation energy decreases, then what do we understand from it? We already studied in our previous class, right? So if a boy, okay, this is the barrier. Okay, so here is a, okay, this exactly is what we studied in our previous class based on activation energy, Arrhenius equation and all of these things. So here this ball has to push this ball to this top, and then from that the reaction takes place. The ball moves quite easily, right? So what am I telling? This exactly is going to be our EA, right? Till here. Okay, this is the activation energy that is required for the ball to be pushed from down till the top of the barrier, and after that it's going to move easily. So this energy is activation energy. When catalyst is being introduced into the chemical reaction, or when catalyst is being introduced here, what do we mean by catalyst is being introduced here? I'm going to reduce the barrier here. This threshold barrier is going to be reduced. So if this is reduced, or let us just draw here with another color, so we are going to, okay, so that we can relate it pretty much well. It's actually same, okay, the product is going to be formed at the same place here. So here now the barrier has been decreased. So if the barrier has decreased, can the boy push the ball much more easily? Yes. Can many people push the ball much more easily? Yes. Here to this barrier, only few people could push the ball, okay, till the top of the hill. But when the barrier has been reduced much more further, we can see, like this boy, there are many more people who can actually push the ball on top of it, and then the ball is just going to flow, and then that's how the product is being formed. So as we can see, the amount, okay, the amount of the reactant forming the product is going to be high. Okay, whatever reactant we are used, almost everything is going to turn into the product whatever we are being expecting with the use of catalyst. So right now we just saw it, how exactly we could relate it to the activation energy whatever we studied in the previous class. Now we shall be seeing with the graph whatever we are going to be plotting based on this particular chemical reaction. So here we know what exactly is there in the x-axis and y-axis, right? We have potential energy here, and then we have reaction coordinate. So what exactly is reaction coordinate? The process of the reaction. And this part is going to be the energy of the reactant. So certain amount of potential energy is being there already for the reactant. Okay, this is ER. This is the energy of the reactant. And when the reactant is going to be turning into a product, it's going to get converted into a product. As we told, it needs to pass a certain threshold energy barrier. So if I'm taking, okay, I'm just using black for the reaction which is used without the use of catalyst. Okay, I'll use a different color for the reaction pathway where catalyst has been utilized. This is going to be our threshold energy barrier. Threshold energy barrier. What do we mean by threshold energy barrier? We already saw it, right? That is the amount of energy on the whole required for the chemical reaction to take place. Okay, activation energy is only so much. Okay, it's just the small part. This activation energy, what do we mean by activation energy? Along with the potential energy, whatever the reactant is having, there's some amount of energy that is still required in order to cross the threshold energy barrier. That is our activation energy. So you can see this is the pathway which I'm marking it here. Okay, this is where the reactant is going to start. The process is going to take place, the reaction process. We are going to provide certain amount of activation energy. It needs to cross this particular threshold energy barrier, and then it's going to form the product, which is here. Okay, so this is the reaction, this is the pathway where the where the catalyst has not been utilized. Okay, now what are we talking? We are talking about how exactly is the reaction is going to be taking place, or how exactly the rate of the reaction is going to be affected when the catalyst is being added. So this dotted line that you see here, that is going to be, okay, this is going to be the pathway in which the reactant is going to be converted into a product. That is, here you can see the activation energy is reduced. How can we tell the activation energy has been reduced? That is because here there is a new pathway which is being formed. When the catalyst has been added, activation energy decreases. That I'll explain you through one more common example. So imagine a person needs to travel from this place to this particular place. Okay, so place A to place B. This is one of the pathway through which he is going to follow. The same way, the same person, when he has to reach to the place B, he can take another route also. Okay, there is a shortcut route also which he can take, probably for which he needs to walk and go. He cannot be using his vehicle for that matter, but he can reach in much more less time. So imagine the pathway is going to be something like this. Okay, it's going to be much more smaller. Okay, when the pathway is being reduced much more, that means the activation energy is actually reduced. Threshold energy, the threshold energy barrier, the entire reaction requires certain amount of energy, right? That entire threshold energy barrier is only reduced. If the threshold energy barrier is reduced, then we can tell obviously our activation energy is also going to be reduced. That is how the rate of the reaction increases much more ahead. Okay, you can see here, if this is EA, then what is going to be our threshold energy barrier? Our threshold energy barrier is going to be this, right? So you can see from the black line, whatever I have drawn, from here to here, the threshold energy barrier is quite high. Now, when the catalyst has been added, threshold energy barrier is reduced, which is here. The same case happens with activation energy. So activation energy was quite high when the reactant, that is without the catalyst, and then the activation energy which reduced much more. You can see here, this is the activation energy. So activation energy reduced much more, which tells us that the effect of catalyst on the rate of the reaction. So the reaction took place much more faster. So here actually intermediate complex theory is being applied. So through this theory, how we can understand is, because of the activation energy which is being reduced, there are a lot of molecules which can actually collide with each other. That is the reaction in the reaction mixture, and they are going to form the product. Okay, that is only because the activation energy over here has been reduced, means the barrier has been reduced, which makes pathway for a lot of reactant molecules to collide with each other and then form the product. Clear? So this is how we can say the effect of catalyst on the rate of the reaction. Here an entirely new pathway has been formed. Okay, entirely new pathway has been formed through which the reaction will take place, and the rate of the reaction is going to be increased. Now we shall see this with the rate expression, whatever we know. Okay, we know that the rate constant, we are basically speaking how the activation energy is going to be playing a role on the rate constant, right? Along with that, we can see how exactly the catalyst also plays a role. Fine. So now K is equal to, we studied this, right? Arrhenius equation is. So we actually saw it here, right? This activation energy we studied in our previous class only. This is where we saw what exactly is going to be our activation energy, Arrhenius expression, from which we got the rate constant as well. So how exactly is it going to be changing, or how exactly can we tell the catalyst is playing a role? We shall see it now. This is what we saw. Now I am telling, if activation energy is being reduced, rate constant increases, right? That is what I'm trying to tell. So you can see here EA, this entire factor for that matter, I have over here negative, okay, minus EA over here. So if just because there is a negative sign over here, when I'm reducing EA further, the Ka increases. If the negative sign was not there, okay, if negative sign was not there, then how is it going to be affecting the rate of the reaction or the rate constant? K decreases if EA has been increased, or we can say as we are decreasing EA, K decreases further. Okay, this can be written this way. If EA is increased, K also increases. If EA is decreased, K also decreases. This happens only when the negative sign is not there. But we know we have a negative sign over here. Just because there is a negative sign here, as the activation energy decreases much further, the rate of the reaction, the rate constant also increases simultaneously. Okay, how can we write it in the rate equation? We know rate is equal to K, rate constant. Okay, if we are taking any reaction, A forming the product. So if I'm taking the reaction A, which is A plus B, which give the product, I can write over here the rate of the reactant. Okay, I'm just taking one particular reactant. Order is going to be any order for this matter. Here we can see as K increases, our rate also increases. This is how the catalyst is going to affect the rate of the reaction. Okay. Now, there's one more thing that we need to see. By any chance, the catalyst is not going to alter the Gibbs free energy. Gibbs energy is not going to be altered at all. Okay, because of the catalyst. And there's one more thing which is not going to be altered because of the catalyst, which is equilibrium constant of a reaction. This is our equilibrium constant, right? K, the constant, okay, equilibrium constant for the rate equation. Here, the equilibrium constant is not going to be altered at all. For a reversible reaction, if we take, I'll write it here, A is going to give B, the same B can give back A. It's reversible reaction. The speed at which A is going to give B is the same speed at which B is going to be giving the A back. Okay, this reaction, the forward as well as the backward reaction, the speed of both these reactions are going to be same. The effect of catalyst is not going to alter this thing. Okay, so our equilibrium constant for the entire reaction, if we see, that is nothing but for forward reaction as well as for backward reaction. Equilibrium constant for the forward reaction and equilibrium constant for the backward reaction. This is not going to be changed at all. It's going to be same. So equilibrium constant is going to be remaining constant itself. It is not going to be affected by the catalyst. It's not going to be altered. Clear? So we studied about effect of catalyst. Now we shall be seeing collision theory for the chemical reaction. So till now we saw how exactly the activation energy is going to be playing a role. Okay, is going to be affecting the rate constant. Now we shall see how exactly the collisions between the molecule, okay, the collision between the reactant molecules, the collision in the reaction mixture, how is it going to be affecting the rate of the reaction? How exactly the rate constant is going to be dependent on this particular factor. So before that, who gave this collision theory? Collision theory was given by Max Schwarz and William Lewis. Okay, in 1916, they came up with the theory which is collision theory. Here, what exactly collision theory says is the rate of the reaction depends on collision frequency. Okay, the rate of the entire reaction is going to be dependent on collision frequency. Now, what is collision frequency? So, collision frequency is nothing but if I'm having we know in the reaction, reactants are there which is trying to form the products, right? The reactant molecules, how will they form the product? The reactant molecules should react with each other. So, this reactant molecules will have certain amount of kinetic energy already with them, right? So, when they are colliding with each other, if the collisions are going to be properly, like it's going to be proper, the collision is going to be held appropriately, then we can see that is going to give the product. If the collisions are not going to be that appropriate, improper collisions are going to be taking place. So if the two reactant molecules are just going to come and just hit, like they're just going to touch each other and go. If this is the thing, it's not like completely hitting each other. It's just going to touch each other and go. So if they are touching each other and going, then the collision is improper collision, which is not going to give us the desired product. That reactant molecule is not going to give the desired product. So collision frequency is nothing but the number of collisions, proper collisions, which is taking place per second per unit volume of the reaction mixture. Okay. So in the reaction mixture, per second per unit volume, how many effective collisions are taking place? This is known as collision frequency. Okay, so the rate of the reaction is actually dependent on the collision frequency. So if I'm taking here the same reaction A plus B giving the product, the rate of the reaction is going to be, as I told, collision frequency here is denoted by the letter Z, right? So the rate is equal to ZAB, that is the collision frequency of the reactant molecules A and B, E minus EA to the power of RT. So you can see on the collision frequency as well. Clear? Now, all the collisions, whatever is taking place, we cannot tell are going to be effective collisions. Okay, so all collisions do not lead to the formation of the product. That is what. Only if there is effective collision, then the product is being formed. If the collision is not going to be effective, then it is not going to give the product. Okay. So based on what can we tell that the collision is being effective? That is based on the threshold energy as well as proper orientation. Okay, so threshold energy means what? As I told you, the molecule in the reaction mixture, reactant molecules will be having certain amount of kinetic energy, right? So this kinetic energy, the certain amount of energy what the reactant molecules will be having, that is called the threshold energy. So if the molecules are having good threshold energy, then they're going to come and they're going to collide with each other very well, which is going to give us the product. If they are not having proper threshold energy, then as they are coming, so the molecules are coming close to each other, they're just touching. So with this, does the collision take place effectively? No. Okay, so effective collision is not being taking place. That is one factor which tells us whether the collisions are effective or not. Along with this, there's one more factor, which is proper orientation. The orientation of a particular molecule, okay, the orientation of the reactant molecules which collide should be proper. What do we mean by that? As I told you, if the energy we spoke about, right, if the collisions are taking place like this, then it is effective. If the collisions are taking place just like touching and they are just moving, they have good energy, they come, they collide, they form the product. Now these are having good energy, but they're not colliding in the proper orientation. They're just going to come, they'll touch each other and they'll just go. So with this, whether the collision is going to take place effectively? No. Okay, the product are not going to be formed. The same thing that they're telling here, proper orientation is very necessary for the collision to take place properly. Okay, threshold energy as well as proper orientation is going to give us the way, like, you know, reactant molecules are going to be breaking the bond and then they will be forming a new bond, forming that is the product. Okay, the breakage of the bond, reactant molecules, and then the forming of the product is going to be taking place, formation of the products. So this is how we can tell the effective collision is taking place. These are called as effective collisions. The collisions where the threshold energy is being met, as well as the reactant molecules or the reaction mixture will have proper orientation between the collisions. Only such kind of collisions are going to give us proper only those collisions are going to give us proper products. Otherwise, we are not going to get a predicted product. Clear? Now we just saw I was just hitting my fist with each other and I was just explaining you, right, how exactly the collision should be taking place. We'll see how exactly the proper orientation plays a role over here with respect to chemical reaction. Okay, so here I've taken an example of formation of methanol from bromoethane. Methanol formation from bromoethane. Now, as we told, CH3Br is here. So there is proper orientation as well as improper orientation. Both the orientations I will show, and I will tell you how exactly proper orientation only is going to give us the desired product. Fine. So here we have CH3Br. CH3Br plus OH. Okay. Now, I have here improper orientation and then here I'll have proper orientation. Clear? So with improper orientation, what exactly is happening? Here our OH is going to go and attack the Br, attack the CH3 plus. Okay, Br is just going to go, OH is going to go and attack the CH3 plus directly from front. Okay, so with this kind of orientation, are we going to get the desired product? Can you all tell? Like, can you all just think about it? Br, right? Here, OH. If it is going to come and try to attack CH3 plus here directly, we already have Br over here, right? Br is going to block OH on coming and directly hitting or directly attacking CH3 plus. So here what is going to happen? OH is not going to be forming the bond with CH3 plus just because Br is there. There's a huge barrier here. How can OH come and attack CH3 plus? It's not possible, right? So with this orientation, we are not going to get the desired product. But now the OH is going to, what the OH is actually going to do is, OH is going to go and attack CH3 plus from behind. When OH tries to attack CH3 plus from behind, what exactly is going to be happening here? Here an intermediate is going to be forming. Okay, so we have OH, right? Here it's going to be OH. OH will be trying to form a bond with CH3 plus. At the same time, there will be bond breaking of CH3 plus as well as Br. Okay. It's going to be an intermediate formation. Here what is happening? Bond breaking is happening. Here what is happening? Bond formation is happening. So this way we can tell when OH is having proper orientation, in a proper orientation, OH is going to go and attack CH3 plus, then only the desired product is going to be formed. What will happen here? As slowly the OH bond is being formed, Br bond will slowly go away. So we can see here CH3OH plus Br minus is going to be given out. So only because of proper orientation, we can tell here the desired product is being formed. Clear, students? So this is how we can tell the proper orientation and threshold energy plays a major role in collision theory, plays a major role with respect to the rate of the reaction. Clear? Now the proper orientation, whatever we are talking about, proper orientation is also, I told you, is also going to be playing a major role in the effect, in the rate of the reaction, right? As the rate of the reaction increases, that means the effect of collisions also should be increasing. If there is proper collision taking place, then only the rate of the reaction increases. So the factor which actually accounts to the orientation of the reaction molecule, reactant molecules, is going to be probability or steric factor, which is denoted by the letter P. Okay, so this is going to be a factor which is going to account for the proper orientations. Okay, if there is proper effective collisions taking place, proper orientation, proper oriented molecules are being colliding with each other, this is some factor which is going to determine this, which is denoted by the letter P, and that's how it is being included in the rate of the reaction. So what did we study in the first? We studied that how exactly activation energy is going to be dependent the rate is going to be dependent on activation energy, right? At the same time, we saw the next thing. Let me write this. The next thing is going to be our collision frequency. How exactly the rate of the reaction is going to be dependent on the collision frequency. And along with that, now we saw the steric factor or the probability. So this also determines the rate of the reaction, as in the rate of the reaction is going to be dependent on the probability as well. What is probability? Probability is nothing but it's going to be the orientation, okay, whether the reactant molecules are having proper orientation while they are colliding. Clear? So this is the last topic of the chemical kinetics chapter. So in next class we are going to be studying basically about the NCERT question and answer discussion. Okay, so the NCERT problems which are present in your textbook, I'll be solving a few of them. Few of them I've already solved along with the example problems. All of these I have already solved in our previous sessions. Now I'll just be focusing on a few more problems which needs to be solved from your NCERT, which is actually important from your exam point of view as well. And along with that, we shall see some of the MCQs, what kind of MCQs can appear from this particular chapter. Clear, students? So we shall meet in the next class. Until then,